let's kick off this explainer with a fact that honestly surprises a lot of new cadets. The magnetic compass out on your bridge wing? It's lying to you, right now. And it's doing it by the very design of the planet itself. So how exactly does a massive steel ship know which way it's actually pointing? Well, we're going to explore the incredible engineering that keeps modern vessels safely on track. To understand the core issue here, you have to recognize that magnetic north and true geographic north are just not the same place. True north is the Earth's rotational axis, right? It's that fixed, absolute point that all your charts and GPS systems reference. But magnetic north, that is determined by the Earth's constantly shifting magnetic poles. And because of this, the amount that these two disagree actually changes depending on where you are on the planet at any given moment. But, there's a second, far more immediate problem for mariners. Think about it. A ship is essentially a massive floating steel city. You've got this huge steel hull, thousands of tons of cargo, running motors, and incredibly dense electrical equipment. All of that creates intense local magnetic interference. And this interference just totally throws off traditional magnetic compass readings even further. On a long transit, that error alone could literally put a ship miles off its intended track. So, the big question is, how does a modern 200 meters steel ship packed to the brim with electronics actually know its heading? The answer is the gyrocompass. It is an absolutely ingenious heading sensor that, believe it or not, has almost nothing to do with magnets. Instead of just passively reacting to magnetic fields, a gyrocompass actively seeks out true geographic north through pure physics, and that is what makes it completely immune to the ship's own steel structure and all those nearby electronics. And the technology behind this has evolved in such a fascinating way. Older mechanical versions basically use a fast-spinning rotor, a gyroscope, mounted in gimbals. The angular momentum of that spinning wheel, combined with the Earth literally rotating beneath it, causes the device to naturally shift, or precess, until its axis aligns perfectly with true north. But those traditional mechanical gyros, they are rapidly giving way to highly accurate, basically maintenance-free solutions like fiber optic gyrocompasses, commonly called FOGs. Now, what is really mind-blowing is how a FOG actually works. It operates with exactly 0 moving parts. It uses something called the Sagnac effect. Basically, it calculates rotation by literally racing light beams against each other. You send light in 2 opposite directions around a coiled fiber. As the ship rotates, those light beams arrive back at slightly different times. By measuring that incredibly tiny phase difference, the FOG calculates the exact heading and rate of turn instantly, no calibration needed. Because it's completely unaffected by all that magnetic interference and always points to true north, this heading data becomes the undisputed truth on the bridge. The gyrocompass acts as the primary reference that gets fed into nearly every critical system on an integrated bridge. Your marine radars for tracking targets, your ECDIS electronic charts, your AIS, they all depend entirely on the gyrocompass to tell them which way the bow is actually facing. This continuous flow of data built an incredibly tight automated feedback loop for navigation. The autopilot relies on the gyro's data every single second. It takes that true heading, compares it against your target heading or the planned track from the ECDIS, calculates exactly what correction is needed, and automatically sends a command down to the steering gear to nudge the rudder. Then the gyro reports the new heading and the whole loop repeats. It constantly keeps the ship on track, totally fighting off wind or current. So the stakes really come down to this. A robust, integrated bridge system is only as good as its heading accuracy. That's it. Everything from your X-band and S-band radar collision avoidance to your automated track control fundamentally depends on the gyrocompass telling the absolute truth. If that heading data is flawed, well, every single automated decision made by the bridge systems is going to be flawed right along with it. But let's throw a scenario out there to really test your understanding of all these integrated high-tech systems. Imagine a total blackout. The ship suffers, say, a catastrophic engine room fire and loses all electrical power across the main integrated network. Every single screen goes dark. What happens to your state-of-the-art fiber optic gyrocompass and the autopilot feeding off it? They become completely useless, instantly. So, when the lights go out, what still gives you a heading? The answer is your oldest friend on the bridge, the traditional magnetic compass. When the screens go dark, the gyrocompass is dead. And that is exactly why international SOLAS regulations strictly mandate that you carry a traditional magnetic compass. Because it requires absolutely 0 electrical power to function, it's your last line of defense. It's the ultimate unpowered backup when literally everything else fails. And this perfectly reveals the core philosophy of maritime safety at work: deliberate redundancy. You see, you don't just want 2 of the exact same system. You want deliberate redundancy between a highly accurate, power-dependent electronic primary system and a completely independent, unpowered backup that would fail in a completely different way. They just complement each other's vulnerabilities perfectly. But wait, remember what we established right at the beginning? The magnetic compass is still profoundly affected by the ship's own steel hull and local magnetic fields. And this is exactly why professional mariners must maintain a deviation card. It's this vital calibration reference, usually created by certified technicians, that documents exactly how many degrees the ship's own structure throws off the magnetic reading at every single heading. It allows the navigator to actually go in and professionally correct those errors manually. As we wrap up this explainer, just remember that understanding this delicate balance is absolutely critical. On one hand, you have the high-tech physics of the gyrocompass seeking true north to drive an entirely automated bridge. On the other hand, standing right alongside it, you have the ancient, unpowered magnetism of a compass needle that has to be carefully corrected for local deviation. Mastering the dance between these two systems, that is the hallmark of a true professional navigator. Which leaves us with this final thought to consider. If your vessel loses all power tonight, and you are plunged into complete darkness, the gyrocompass is gone. Your integrated bridge is completely blind. Are you prepared to trust your life and the safety of a 200-meter floating steel city to a simple magnetized needle and a paper deviation card? It's definitely a sobering reminder of why mastering the fundamentals will always, always matter.